for my own. Okay. So we are going to be talking about concept bottleneck models in this lecture. Concept bottleneck models, we are going to look at it through three papers today. The first two of them we will look at in detail, but the third one we will be looking at a little bit superficially. And then we will talk about concept or information leakage problem. And then I will categorize CBMs into top-down and bottom-up, and I will end up with a bottom-up CBM, which is called Discover Then Name. So please interrupt me if you have questions, okay, anytime. So the motivation behind CBMs is very clear. Most visual recognition models operate as black boxes. Your favorite image classifier, whether it's Dino V3 based or clip based or I don't know, anything you mentioned, or your vision language model, they all operate as black boxes, which means their internal reasoning is opaque. Decisions cannot be inspected or interrogated, but we know that the transparency is very important for a couple of reasons, especially for the topics of this class. Transparency is essential for fairness, accountability, interpretability, and intervenability. The first three terms are probably very clear for you, but the fourth one may be a little less. Intervenability means the capability of intervening the decision process of the model. So you, at an intermediate layer, you open up the model and you tweak something, and then decision changes. So that's what we call intervention. CBMs offer a structured solution to this problem. It bases its decision on human understandable concepts. And by doing so, it enables explanation, diagnosis, and control. It provides explanation because, as I said, there's an image classification result at the end, but it bases its decision on human understandable concepts at the intermediate layer. You can you can make diagnosis when there is a, for example, incorrect prediction. You can see whether this incorrect prediction is caused by a specific concept prediction in the bottleneck layer. So you can debug the model, debug the decisions of the model, and also you can control. So if you are an expert in that classification task, you can go to the bottleneck layer and change the concept activations, and then this changes the prediction or decision of the model. So CBM originally was proposed in this paper, ICML 2020, and here is the teaser figure for that from that paper. And as you can see, input is an image, and it goes through a CNN, which outputs the concept activations. In this case, this is a medical image understanding task. This is an X-ray image, and the concepts are medically related concepts. And then the image is first mapped to activations in this concept space. And then in the second stage, these activations are converted to a class decision, or in this specific example, a regression decision. Sorry. It's a grading task on severity of some knee problems. In the second example, the bird image is projected onto, again, a relevant set of concepts related to birds. And then the second stage model, which is called the classifier here, based on the concept activations, produces a prediction, which is about the bird species. So if you if you did some computer vision research in the early 2000s, you will realize that this kind of thing is not new, because we had attribute-based classifiers since early 2000s. And for the related work based on attribute-based models, you can check the paper. Sorry. What these CBMs bring new is the promise that they can convert any vision encoder to an explainable model. That's the promise of CBMs, and that's what sets it apart from the attribute-based classifiers in the early 2000s. And how they achieve this is, again, we have the input image X here, and you have, for example, a CNN. It could be a VIT, any vision encoder model, and you have the category prediction, right? Y hat. What this paper does is takes an intermediate layer, for example, a layer here, and then resize it to output the concept activations, and then introduce a linear classifier or a shallow classifier to output Y hat, and they're not using this part anymore. So this is the recipe proposed in this paper to convert any vision encoder into a concept bottleneck model. Of course, you have a loss, a concept loss to make the concept predictions here as close as possible to the ground truth concept annotations, and of course the usual classification loss, which takes the ground truth label and the predicted label, right? This is how they convert any given vision encoder to a concept bottleneck model. So if we mathematically define it, again, X is our image here. So X is our image. The first transformation, H, takes the image and converts it into concept activations, C hat. And this is a real vector of size, let's say capital K. And capital K here is the number of concepts. And then the second mapping, G, takes the concept activations and produces the class prediction, predicted label. And as I said, we have concept loss, which takes HX and minimizes the discrepancy between HX and the ground truth concept for this specific example, plus some weighted term, the task loss, which is classification here. It's G of H of X and Y, okay? So this is the mathematical description of a CBM. So you can do lots of things differently here. For example, your concepts, you can define your concepts to be hard concepts like binary concepts, whether it exists in the image or not, 0, 1, or soft concepts, some with fuzzy existence. You can train this part first and this part next, sequentially, independently, or jointly. So there are lots of things you can do. There are lots of variations you can achieve this concept bottleneck model. In this original 2020 paper, they assume that each training image is annotated with concepts. That means our training set, image classification data set, or the regression set, not only has the XY pairs, but X, C, Y triplets, okay? And this is a major limitation of the original CBM work. you assume that the concepts are annotated for you by some human expert, which is a costly thing to do. But let's assume that we have the annotations. They use two data sets in this paper, X-ray grading and the bird classification data sets. And here, this is the main table of the paper. They show that for the regression task, this is a regression task. They assess, predict the grading severity of some disease from 1 to 5, I believe. So it's a regression task. But the bird classification is the classification task. So for the first task, here you see the results, and the first 3 rows, these are the CBM results, and these are the standard black box, classical black box image classification methods. As you can see, the error is even lower than the black box method, so it does a good job of, it even outperforms the classical black box methods, and it brings explainability. That's the main promise of the paper. On the CUP dataset, bird classification, again, the errors are low, but this time the black box methods are lower here. But they say that it's close to the black box method, and the additional benefit is that CBMs can bring explanation. They can do test time intervention. This is a nice property of CBMs. For example, if you are a medical expert, if you're a radiologist and trying to decide the grading of some disease, and let's say you feed this X-ray into your CBM, and this CBM produces the concept activations in the first stage. And you might say, as a medical expert, that this specific concept, such as this joint space narrowing, is it should not be as high as the first stage says. So you can intervene to the model and change this 1.69 to 1. You can reduce the concept, activation of the concept. And then this eventually changes the decision from a wrong decision to a correct decision. Similarly, you can say that as a medical expert, some specific concept is not correctly detected by the model, and you see the image and you can just say that this concept is there, bone spurs, and then this again corrects the decision. They repeat the same intervention with the birds too. This time they intervene with not just a single concept, but a group of concepts. For example, all the concepts that are related to the tail of the bird. And when they change it, they show that the prediction becomes correct. And there's another example in a similar manner. So they are saying that CBMs allow test time intervention. If you are an expert in this task, you can examine the concept activations and change things, whether this concept is highly activated, more than necessary, you just reduce it, or the other way around, and then you see its effect on the prediction. They also show, interestingly, some data efficiency results. You can think of it as few-shot recognition on the left. So you see here the standard model, which is the black box standard ResNet training. The error is higher than the CBM errors, and when you use a small percent of the training data, which is the few-shot regime here, the CBMs are much better than the black box method. So they are saying that when the model is forced to concentrate, focus on concepts, the data efficiency is better. You learn more with less number of examples. On the bird data set, it's less pronounced, but still the standard model, the purple one, there's a gap between almost 10%, more than 5. There's a gap between the CBM and the standard model. Again, CBM has a lower error in the few-shot regime. But if you look at the full data set, when you use all of the data set, you see that the standard model, black box model, is better in terms of accuracy or task error. Another interesting result that they show is the robustness to distribution shifts. They tested by changing the background of birds. In this bird data set, they have the segmentation masks of the birds. And what they do is, for a certain class, in the training, they put the birds on a certain background, which is, in this example, they put this black-billed cuckoo images to forest backgrounds. But the same class in the test set is pasted onto different backgrounds, like coffee shops. So they are now testing whether the model focuses on the correct features of the image, such as the bird, and not the spurious correlations, which is the background in this case. And they show that CBMs outperform standard resident training on this task. And they say that the standard training focuses too much on the background. It takes a shortcut, but CBMs, because it forces to concentrate on the relevant concepts, it does a better job in robustness to background shift. So this is all good, but there is a major weakness, as I mentioned at the beginning. This paper assumes that each example in the data set is annotated with concepts, which is a huge assumption, actually. Consider ImageNet, which is a large-scale image classification data set. Annotating each image with a set of concepts is a very difficult task, very time-consuming task. And if you want to do this for all image classification tasks, it's not easily scalable. So that's a major weakness. But the subsequent CBM papers, fortunately, addresses these weaknesses with the help of VLMs, vision language models such as CLIP, or large multimodal models such as LAVA. I'm sure all of you are familiar with CLIP, but let's remember what CLIP gives us, what capability gives us. So in CLIP, which is a VLM model, vision language model, which was trained on massive amounts of image caption data, which are collected from internet. So this model is trained on internet scale data. So it's a massive model trained on a massive data set. What you can do with this is you feed the image to the image encoder, and then for the text encoder, you can feed anything you want, any text you want. And here, if you feed the concepts, let's say you have a concept set coming from some dictionary or some expert has given you a list of concepts. You give the concept list here, and then with CLIP, you can measure the similarity of this image with the concepts in the concept set. Okay, and this provides a kind of labeling of the image with the concepts. Now we don't need a human annotator to annotate this image with the concepts. You can use CLIP to annotate the image with concepts. Now we can do this. It provides us the concept annotations. Now we can go back to our CBM and train it using CLIP provided annotations. And the label-free CBM, which was published in ICLR 2023, achieves exactly that. So they can take any neural network backbone, they call FX. So you can use Dino V3 here, you can use perception encoder, CLIP vision encoder, whatever you want. That's the nice thing about CBMs. You take any vision encoder, and then you can convert it to a CBM, and this conversion is fully automated. So there is no human intervention is needed. No concept labels are required, so you don't need a human annotator. That's why it's efficient. And it's also scalable because this is the first paper or one of the first papers to show that CBMs can scale to the ImageNet scale. Because the previous ones, the 2021, only showed on the knee X-ray and the birds data set. These are small tasks compared to ImageNet. So this paper was one of the first to show that CBMs can scale up to 1,000 classes and still provide good results. So how they do this, there is a 4-step process here with label-free CBM. Now I'm going to go over each step one by one, and then hopefully we will understand how label-free CBM works. So let's look at the first step. The first step is concept set creation and filtering. Here, they take, and so the task is image classification. Again, you take the ImageNet data set. What you know here is the images and their labels. You don't know anything else, right? So you take the list of class names and use those class names and ask GPT, it was GPT-3 back then. You can use ChatGPT for this now. You ask these questions to the LLM. You say that list the most important features for recognizing something as a class. So you do this prompt for each of the 1,000 classes, and then LLM gives you a list of concepts, right? And then at the end, you get thousands of concepts, a huge list. Later, they have some filtering steps. They, for example, remove redundancy by removing duplicates or very similar ones. They remove class names. They remove very long ones, very short ones, etc. But they do some filtering. But at the end, if I remember correctly, there is like 4,700 concepts for the ImageNet dataset. They come up with 4,700 concepts for the 1,000 classes in ImageNet. So this is the first part. Now we have a list of concepts, thousands of them. The next step will be you are going to use clip, which is this part, the lower part here. You are going to use clip to create the concept annotations. They call it concept matrix here, the P matrix. So your images go through the image encoder of clip, and these are frozen. They don't, these are not trained. They take a trained clip off the shelf, and they feed the images to the image encoder and the concept list coming from GPT to the text encoder. And at the end, you get this matrix P, which is the rows is the number of images. So in the rows, we see the images, and in the columns, we see the number of concepts. So now you have a number of images by number of concepts matrix, and in each cell, you have the similarity of that specific image with the specific concept. Now you treat these as the concept labels of images, and the next step is to learn or so learn a model that predicts this matrix P for the data set. And they achieve this by training a linear layers, this WC, now step 3. So remember, X was our image, and FX is the backbone features. It could be Dino V3, it could be any vision encoder you want. Now what they learn is this linear layers, WC. You learn WC, and then you need to have a loss function between this and P, right? P has the image concept similarities. FCX now predicts those similarities. Now you need to have a loss to reduce the discrepancy between P and FC of X. And this is what they use on the right-hand side. They call it cosine cubed similarity. The cube is used because for the purpose of exaggerating the highly activated concepts and suppressing the lowly activated concepts. That's why they use this power of 3. And basically, they are trying to maximize the similarity values in matrix P by learning this WC. This is what is being done here. And for this step, different CBMs use different loss functions. You can even use a mean squared error here, MSE loss, because what you want is FCX values to be as close as possible to P. You can use even binary cross entropy and so on. Different CVMs use different losses. Okay, now we learned the matrix that predicts the concept activations given an image. Final step, step 4, is the learning the final sparse classifier, which is learned here. And they learn again a shallow network here, just one linear layer, and its weights are WF. There is sparsity regularization here as well. They enforce sparsity here because for a given image, you want explanations to be sparse. There should be a few number of concepts that explain an image, not just hundreds or thousands. Usually people prefer 5, 10 concepts to explain one image. So this is the usual cross-entropy loss. And this is the regularization that enforces sparsity on the final classifier. Okay. Any questions so far? So label-free CBM is actually very easy to understand. And their results are, as I said, one of the first large-scale results. They show results in ImageNet, places 365, which are large data sets, but they also show results on classical smaller data sets as well. And they show that, importantly, they show that their CBM achieves 71.95, 72% on ImageNet, and they are saying that the gap between the black box models, the standard ones, and the CBMs has narrowed, which is a very successful result, by the way. CBMs usually have this accuracy gap between the standard black box models. So when you force explainability, you trade off some accuracy with explainability, but they show good results overall. Yeah. So standard means here, it's not a CBM. So, oh, you mean this one? Standard sparse. I need to look at what that means. It's a CBM. It's a post-hoc CBM, it's called. So it's an earlier model, and they don't provide any results for the large data sets. But yes, I don't know. I have to check this. Yeah. But the main comparison is between the black box and the CBM and other CBMs. Yeah, I don't know the standard sparse. Let's check the caption quickly. You can see. I think so. It's a standard image classifier with sparsity regularization. I think that's yeah. And it's worse than the standard ResNet. See, it's a little bit worse. They show interesting explainability results. For example, if you take an orange object and a lemon object, they show how the concept activations are distributed for these two predictions. For orange, you see the bright orange color, citrus fruit, and for lemon, also citrus fruit, but now it's lime juice, yellow color, and so on. So the explanations make sense. It's really good. There are lots of qualitative results in the paper. You can check. The explanations are usually quite good. So At the same time with LFCBM, there are other proposals which try to address this lack of concept annotations. And one of them is the CVPR 2023 paper, abbreviated as LABO. This is abbreviated as LABO because of this title, Language in a Bottle. And they do a very similar thing. They feed the class names, not the images. This figure shows that they feed the images to LLM, but they don't. They feed the class names. Again, class names, LLM provides you some candidate concepts, and they have a concept selection stage where they select concepts based on their discriminability and removing redundancy. And at the end, they have a concept list which are encoded by the clip text encoder. So you have this EC now, the concept space, which are the clip embeddings of the concepts. And for classification, you take the dot product of the image embedding with the concept embeddings, and this gives you the concept activations. And then you multiply this with the class concept weight matrix, which is learned. So this part is learned. So it's actually very similar to LFCBM, and there are only small details that are different. This paper shows very good few-shot recognition results. So if you look at, for example, CIFAR on top right, when you use one shot per class, look at the gap between the classical linear prop, which is using the same vision encoder as LABO. There's a huge gap. And with 2 shots, 4 shots, and at the full shot, the whole data set, the accuracies are the same or very similar. But usually the CBMs show great data efficiency compared to their black box counterparts. It's a very active area of research. After this 2003 papers which used VLMs, clip-like VLMs, other papers, for example, this one in ECCV 2024 uses large multimodal models. They specifically use LAVA here. So this multimodal LLM is LAVA. So they basically ask give the image to LAVA because LAVA can recognize images, and ask the questions, does the object have attribute A? Now we see that previously we were feeding only the class names to the LLMs. Now we are feeding images as well. And this gives us, they are claiming that this gives us better concept. It's more grounded in the image content. Another proposal, this NeurIPS 2024, it's called VLG CBM. They do a very similar thing. They start with a very large concept, a candidate concept list, and then they use open vocabulary object detector here. They use specifically grounding dyno. So which basically tries to detect objects with an open vocabulary. So you ask any concept name and it tries to find the object in that image. And if something is detected by grounding dyno, they automatically label that image with that concept. So at the end, they form this image concept class label or box concept class label triplets, and this constitutes the training data set. And then the rest is almost the same with LFCBM. It's actually the same authors, the same team, but only the concept labeling part is different. So it's a very hot research area today. You can see lots of many other CBMs, but the overall steps and overall challenges, tasks are very similar. As you can see, you use a VLM or multimodal LLM to get your concept labels, and then you somehow learn the concept predictor and then a classifier. So these steps are common to all CBMs. So there is a serious problem with concept bottleneck models, which is called the concept leakage problem, or some papers call it information leakage problem. And this problem is the following. CBMs show unexpectedly high accuracy when using irrelevant concepts for the task. So, for example, let's say we are trying to solve ImageNet classification task. As you know, it has 1,000 classes. There are visual object categories. But let's say you use concepts coming from Roman law concepts, which are, you can say that this is irrelevant to images, because in Roman law there are concepts like, I don't know, Roman law concepts. They are not ImageNet objects. So Roman law concepts is an irrelevant concept list. But when you use this concept list with ImageNet, you get a high accuracy. And this is unexpected. You don't want your CBM to give high accuracy with irrelevant concepts because your explanations are not correct, because they are irrelevant. And this problem is first identified by these two papers, and this is still an open problem. People are trying to address this problem with recent works, so it's still a major and open problem. It's well known, and I'd like to show you why this thing is happening. So let's say we are working, so for ease of illustration, let's say we are looking at a two-dimensional clip embedding space, okay? Of course, the clip embedding space is huge, hundreds or thousands of dimensions, but for simplicity, let's say we are looking at a two-dimensional one, and suppose that this dot is our dog image, and this is our cat image. So we are trying to develop a CBM for cat and dog classification, okay? Now, if you use a relevant concept set, you will have some set of concepts that are related to dogs. Let's call this to dog concepts. And we will also have some concepts related to cats. So there are these dots here are, each of them is a concept, and you pass it through the clip text embedding encoder, and now you are in the same space with the images. And because these are relevant concepts, the distances or similarities to the images are, similarities are high, distances are low, okay? And what a CBM does is to represent this cat image by the similarities to the concepts. So you take the similarity of this image with all the concepts in your set, including the dog concepts and cat concepts, and this set of similarities is now your feature vector for the second stage classifier. You do the same with the dog image as well, and you get these concept similarities, and you train a classifier. But what happens when you use an irrelevant concept set, let's say Roman law concepts? They are, let's call these Roman law concepts. And here each dot again is a concept. Now we have a higher distance between the Roman law concepts and cat images, dog images, of course, because they are not relevant. But still, these distances encode information that can be used for classification. So even these are irrelevant, the classifier can use those irrelevant, so distance to those irrelevant things, it can still learn a good classifier. And this is called the concept leakage or information leakage. So the solutions to attempts to address this either, so solutions, not solutions, but attempts, let's say, because it's still open. They either restrict the concepts that are used by a similarity threshold, right? Because if you enforce a image concept similarity threshold, and if that threshold is optimal, then these Roman law concepts will be just rejected. They won't be used. And your classification accuracy will suffer, of course. But this is what we want. If I use an irrelevant concept list, my accuracy should be low. Or you use top K small, like 510 concepts per image. This is also a used method to address information leakage, because when you reduce the number of concepts, the ability to classify using irrelevant concepts reduce. Okay, but these are not ideal solutions. These are just solutions, and the community is still trying to figure out how we can address this leakage problem in a better way. So finally, let's look at the top-down versus bottom-up distinction, and then I will give an example for a bottom-up CBM, and we will be done for today. Top-down CBMs, externally, in the top-down CBMs, we use externally specified concepts, and these are provided by either humans or models such as LLMs. In bottom-up CBMs, concepts are discovered during training from image content. Okay, this is the distinction. In the top-down, which so we have seen 3-4 CBM examples so far, and they are all top-down because we give the concept set obtained from LLM, right? So concept set is designed before training the CBM, and this is a flexible approach. I can use Roman law concepts or even random strings for an ImageNet classification. So this is very flexible. But in the bottom-up concepts, the concepts emerge automatically during training. Usually, a sparse autoencoder or a similar dictionary learning method is trained to reconstruct clip embeddings or the backbone features. Units in the learned dictionary correspond to interpretable directions. Hopefully, they don't always correspond to concepts, but they often align with semantic attributes, and concept naming is done after this. So concept naming is done after the concept discovery. And I think the canonical example for bottom-up CBMs is this ECCV 2024 paper, which is called Discover Then Name. It has 3 steps. The first step is automated concept discovery, where you feed your images, only images, no labels, nothing, to the clip vision encoder, and you get the clip embeddings here. These are clip embeddings. What you do is to train a sparse autoencoder to reconstruct the clip embeddings. And usually the intermediate layer in the sparse autoencoder is much larger than the clip embedding. If you have a 768 dimensional clip embedding, this is 8 times 700 as many nodes here, because they try to disentangle the concepts within the clip embedding. That's why they need a larger bottleneck layer. It's not a bottleneck, but intermediate layer. So they use a sparsity loss because they want as few concepts as possible activated per image, and there's a reconstruction loss, of course, as usual. They say that the concepts learned in this intermediate layer are the disentangled concepts within the clip embedding, and then now we can, and they claim that each of them corresponds to a semantic concept or attribute, and to name them in the second step, they take this linear decoder in the first stage, because this is just a matrix, okay? And the columns of these matrices are actually the elements in your dictionary. And what they do is, so they take this decoder here, this is the learned decoder in the previous step. You take each column and you check the cosine similarity of that column with the clip text embedding of a list coming from, again, externally. we said this is bottom up, but you still need a list to name them. But this list can be everything in an English language. So this is not a specific, a curated set. It's not a curated set. So you assign each dictionary vector to a class concept name, and this part is the concept naming part. And then the third step is to obtain the concept bottleneck model. Again, they use clip vision encoder. This time they take the encoder here and they learn a linear classifier at the end, which uses the discovered concepts. This is an example for the bottom-up CBMs. So, yes. Yes. So the bottom-up part is this sparse autoencoder here in the intermediate layer. These nodes correspond to disentangled concepts, and these are discovered from image content. They use the frozen clip encoder and their learned linear encoder. So this one, linear. Again, there's the classification as sparse loss. Yeah, this is discovered and named. And there are lots of SAE, sparse autoencoder based concept models out there. So as a summary, concept bottleneck models convert any vision encoder to an explainable model, and they provide explanation, diagnosis, and control. Questions, comments, we can discuss. Yeah, can you say that how many papers? Of course, yes. And yes, there are, I think, CBMs on language data from them. It's kind of the concept itself, you have each allocation as classes. Okay. Yeah. Yes, there are, and this one is, I think, close to what you are asking. So this is not a segmentation mask, but this is an object detector. It finds bounding boxes, and within that bounding box, grounding dyno gives you a concept name. It detects something there, and that is how you find the concept, localize the concept. Yeah. But segmentation-based concept, maybe there are, I don't know. There are CBMs that try to locally, spatially ground concepts within the image. So I think there should be some segmentation-based one as well. Teşekkürler. Evet, Alfa kullanıyorsunuz burada şey mi?